For 70 years, the goal has been bottling the power of the stars here on Earth. It is a pursuit so notoriously difficult that it created a long-standing joke. Fusion is always 30 years away. The atomic hurdle is specific. A deuterium-tritium reaction requires forcing two isotopes to fuse, yielding helium and a high-velocity 14.06 mega-electron-volt neutron. This period of research focused on gathering raw experimental data. It was a necessary physics era, where the priority was understanding particle behavior rather than generating usable electricity. Today, global energy consumption is rising, driven by hyperscale data centers and AI models that require uninterrupted, carbon-free power. This demand has created a commercial pressure that is shifting fusion from a scientific curiosity into a strategic priority. Because of these energy requirements, the technology is transitioning out of the laboratory. It is now being developed as a deployable utility. The UK government is centering this transition on a £1.3 billion fusion strategy, managed by the state-owned firm UK Fusion Energy. The physical footprint of the project is visible across the country, as legacy research sites are built out into expanding industrial hubs. The primary project within this strategy is STEP, the Spherical Tokamak for energy production, which is scheduled for construction in Nottinghamshire. While previous machines like ITER were designed as physics experiments, STEP has a distinct mandate. It is being built as a prototype commercial power plant. The roadmap centers on a specific target: delivering reliable electricity to the national grid by 2040. Moving from planning to construction introduces complex logistical realities, as the industry attempts to build a fusion ecosystem that has never existed before. The engineering challenge is one of scale. Commercial reactors must be powerful enough to sustain reactions, but compact enough to be economically viable to build. To address these hardware requirements, the UK awarded a £70 million engineering contract to the private firm Tokamak Energy. They are tasked with developing high-temperature superconducting magnets. These magnets are required to contain plasma within the unique spherical design chosen for the STEP reactor. Integrating private firms into the core design of the machine aligns fusion development with the patterns seen in other mature industrial sectors. Managing a commercial plant also requires solving a critical software problem. Millions of interdependent parts must work in unison to stabilize plasma that is inherently chaotic. A £30 million contract was awarded to Dassault Systèmes to develop the digital infrastructure needed to manage these complex systems. Engineers use digital twins to optimize the device. These virtual models let the team stress test the reactor's life cycle before construction begins. Within this framework, artificial intelligence is used to predict and mitigate disruptions, autonomously correcting magnetic fluctuations in real time. Solving these software and AI challenges is as vital as the physical magnets in ensuring a reactor is reliable enough for grid deployment. These contracts are the first steps in a larger organizational strategy designed to move the UK's fusion sector toward full commercialization. The objective is to build industrial capacity and a specialized domestic workforce that can compete on a global scale. If the roadmap is successful, the UK will move beyond simply using fusion power. It would become a global exporter of fusion technology, components, and intellectual property. The long-term goal is energy security that is decoupled from the volatility of fossil fuel markets. With sites selected and supply chains activated, the era of the science experiment is fading. The race to power the world with fusion has begun.